Okay, so this video is going to be about horizontal projectile motion. So we've already seen vertical projectile motion, and vertical projectile motion, if you remember, was we have this orb, and it gets thrown up in the air, and it might do something where it goes up and up and up, and then up here we know its velocity is equal to 0, but we still know the acceleration is equal to that negative g, and then it comes right back down. So on the way up, it's slowing down, and on the way down, it's speeding up, and that just moves in one actual dimension of motion. It goes up, it goes back down. So the next thing that we're going to talk about is getting ready for something called two-dimensional motion, which basically means that we are not restricting it to go forward, backward, up, down, left, right only. So if we have our object, I'll put it in red this time, our red orb, and let's say this red orb is rolling down a table or a ramp or something like that, and it reaches the end, and it goes off of the table. So it comes to here and it goes off. So the thing is that we know once it leaves the table, we know gravity's pulling down on it. There's an acceleration out here that, and I'm going to put that in a different color. There's an acceleration out here that is equal to that negative g. But we know that acceleration is downward. And there's nothing really going forward or backward or on the screen left or right to try to get this object to change its motion. So we know if we had actually just dropped that object, so the object started here, we dropped that object, in the first second it might come here. In the second second it might come here. And of course, well, it's speeding up, so it's traveling a bigger distance. In the third second it might come down here, and in the fourth second, assuming that this is a very, very tall table, because it wouldn't take 4 seconds to drop, then it would just keep on going. So actually, this one is not long enough. It would just keep on going off the screen. Okay, but that's because acceleration downward is causing this to speed up. But what if we just rolled it across the table? We actually have already seen it. Rolling it across the table, it's constant velocity. It's not constant acceleration. It just stays at the same speed. So if I were to just have this roll across the table, or just go outward, track it outward, it would go the same distance. So here we have velocity outward in the first second, velocity outward in the second second, velocity outward in the third second, velocity outward in the fourth second. So these two motions will combine and give us the actual path of the object. So in that first second, it appears right here. In the second second, it would appear right here. Okay, I'm switching back and forth between colors, so give me a second. So there we go. In the third second, it would appear right here. Okay, and you might be able to tell that we start to get this curvature going on, and we do the actual path of it in blue, so we get this kind of curvature, because we would know that 4 second would be even down, further down. And that curvature might actually look familiar to you. It is a parabola, and that parabolic motion comes from the idea that we have two different motions going on. We have acceleration in the vertical direction, but we have a constant velocity in the horizontal direction. So we have constant acceleration in the vertical, we have constant velocity in the horizontal. Okay, but if we have the exact same acceleration in the vertical direction, and we don't change the height of the table, then that means it should take the exact same amount of fall, or amount of time to fall, no matter how fast this thing is coming off. So if we had a table that always stay at the same height, much like your lab tables, and we have a velocity, or a ball that's coming off with a small velocity, okay, it would follow a path that might look something like this and hit the ground there. But if we had a much bigger velocity, then the same ball, the same orb, might come and hit way over here. But the thing about it is that both of them, because they're coming off the table horizontally, both of them start off with the exact same initial velocity in the vertical direction, or in the y direction, of 0. And since they are still subject to that same acceleration of negative g, and this distance doesn't change, then the time that it takes to fall here is going to be the exact same time it takes to fall here, and really it's the exact same time it took to fall for just the one that was coming down, just straight down. So what we're saying here is that with horizontal projectile motion, whether we drop an object or launch an object horizontally, which means straight outward, then it's going to take the exact same amount of time to fall, no matter what the velocity coming off. So later on, we're actually going to take a look at the relationship between that velocity, the velocity in the x direction, I'll make a better x here, the velocity in the x direction, and this horizontal distance that we are calling x here. Okay, we're going to look at that relationship. But right now, the key aspect is that only the motion in the vertical direction, only this stuff in the green over here, is constant acceleration. I'll put that in green. Okay, only the up and down motion has that acceleration, while only the forward and backward has that constant velocity. And when you put that together, you get the actual motion of an object, which is a parabola. So I'll put some questions after the video. There's not much to this one, just the horizontal projectile motion stuff. And we will talk about it in class later. Thank you.